So, with that in mind, let's go to 2 dimensions. And in 2 dimensions, of course, our state space is xy. And our differential equation is, of course, 2 variables. X prime is some function of xy, and y prime is some other function of xy. So the first question is, what is the definition of an equilibrium point in 2D? And the answer is, an equilibrium point is defined as x prime equals 0 and y prime equals 0. In other words, f equals 0 and g equals 0. And we find the equilibrium points in the same way by setting f and g equal to 0 and then doing a lot of high school algebra to figure out what values of x and y satisfy that. And then we have the question of stability. And stability is going to be a lot trickier in 2D than in 1D. First of all, in 2D, we can always use test points, but unfortunately here, test points may not be decisive. Here are some test points. Is this equilibrium stable or unstable? Are those arrows going into the equilibrium point, or are they going away from the equilibrium point, or are they doing neither? And the answer is, on the basis of 4 arrows, you can't tell. So if we're going to use test points in 2D, we have to have a lot of them. And you have to take a very short delta t, and you have to really trace out that trajectory very closely and see how it's going. And then once you do that, you say, aha, that's a stable equilibrium, they're headed in. Or it's an unstable equilibrium, they're headed out. So we can still use test points, but we really shouldn't think of them as test points. We should really think of it as plotting the whole trajectory near the equilibrium point and seeing whether it comes in or goes out. That always works. Then you want to ask, well, what about this principle of linear stability analysis? We like that. And we would like to take the linear approximation to this 2-variable system, which means we would like to take the derivative of this 2-dimensional function and set it equal to 0. But the problem is we don't know how to take the derivative of a 2-dimensional function. We've only learned how to take the derivative of a 1-dimensional function. And the solution to this is there is such a thing as the derivative of a 2-dimensional function. And we're going to be covering that in 30b. And we will finally complete this picture at the end of 30b. By showing you how to take a linear approximation to a 2-variable or a 10-variable system. And that will complete that whole thought, but right now we don't know how to do that. So right now we're just going to focus on equilibrium points in this 2D system, but we still have this wonderful principle that equilibrium points are linear equilibrium points. So now let's start to take a look at what some of them look like. So the easiest way to make an equilibrium point in 2D is to take 2 1-dimensional differential equations and mix and match them. Just stick them together. So suppose, for example, we take x prime equals kx, and as usual, I'm going to assume k is positive. X prime equals kx, y prime equals, let's call that k1, and y prime equals k2y. So what is that going to look like? Let's draw the xy axis. And we know that on the x-axis, x prime equals k1x. In other words, this is an unstable equilibrium point because of the positive k. It's an unstable equilibrium point in the x-axis. So the arrows are going to go like this. Classic unstable equilibrium point in x. Now what about y? Well, the same thing. It's an unstable equilibrium point in the y-axis. And so we have just made an unstable equilibrium point in 2D because these arrows are going to go away, 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 away. And they'll be straight if k1 equals k2. If k1 is not equal to k2, they'll be curved a little bit as one of them goes faster than the other. But all arrows are going away. This is a classic, simplest possible example of an unstable equilibrium point in 2D. Okay, same argument. Let's change the model now. So it's x prime equals minus k1x and y prime equals minus k2y. What is that going to look like? Well, again, here's the xy. In the x dimension, it's a classic stable equilibrium point. In the y direction, it's also a classic stable equilibrium point. And so this is going to be a stable equilibrium point in 2 dimensions produced by this 2-dimensional differential equation. So here are 2 simplest equilibrium points by kind of trivially combining an x and a y. And of course, this is an unstable equilibrium point. And continuing our metaphor from the last session, we can think of the unstable equilibrium point as a ball on a hill. And the ball on the hill can roll down in the x, rolls away in the x direction, and it rolls away in the y direction, and that's an unstable equilibrium point. Conversely, here is the classic stable equilibrium point, which we're going to represent as a ball in a bowl, a truly 3-dimensional bowl. And the ball can roll, is stable in the x direction, and you can't see the y direction, but it's stable in the y direction also. Whereas here it's unstable in the y direction. So those are 2. Those are pretty trivial. Here's a really, really interesting and important one that we have not seen before. And I want to think about now x prime equals minus kx, y prime equals plus ky. And again, this can be k1 and k2 if you wish. Now, what is this? Well, in the x direction, it's a stable equilibrium point. In the y direction, it's an unstable equilibrium point. And this is a new animal. So the trajectories here are going to go like this, they're going to go like that, they're going to go like this, and they're going to go like that. And so this equilibrium point is a new kind of equilibrium point. If we have to draw the surface is neither a hill nor a bowl. The surface is like a saddle, a horse saddle. You know, the horse's head is here. So here is the horse saddle, and I want you to think about a ball at exactly the center point of the saddle. So is that stable or unstable? Well, it's stable in this direction, that is the x direction, but it's unstable in the y direction. So a ball at the center of a saddle will roll into the center along that axis, but it will go away from the center along the y-axis. And this is a new kind of unstable equilibrium point, and it's called a saddle point. And so saddle points are one stable direction, one unstable direction, and they are, of course, unstable equilibrium points because if you start near it, you go far away. So it meets the definition of an unstable equilibrium point. So these three examples, the purely unstable, the purely stable, and the one unstable, one stable, giving you a saddle point, these are the three types of simple linear equilibrium points, and therefore the three simple equilibrium points, period, because once again, all equilibrium points are linear equilibrium points. These are the three simple equilibrium points that can occur in 2D by mix and matching 1D vector fields. So we have the three simple mix and match two 1Ds to make a 2D. And that gives us a purely stable, a purely unstable, and the saddle point unstable. But there are other equilibrium points in 2D that are not just mix and match two 1Ds. And in order to show you an example of that, I have to go back to the second week of the class and remind you of an example, and we'll have to rederive the differential equation because I want you to understand it. You recall that we talked about a spring. And the spring is right here, and it is attached to a mass, and we record the position and velocity of the spring, and we put little wheels on the cart there, so it only goes back and forth in the x direction. And the question was, what was the vector field? What was the model of this system? And the answer is x prime equals v. V prime equals the spring force. Change in velocity is acceleration. Newton's law says acceleration is force. Force is the spring force. And we assumed in this case that it was a very simple linear spring and that the force acted against the velocity, so that if the cart is over here in positive x, the force is pushing it into negative directions. So we have v prime equals, x prime equals v, v prime equals minus kx. Let's let k equal 1 to make things simple. So that's now minus x. And the question was, what was the vector field if this is the xy, or excuse me, xv coordinate system? Then we graphed a bunch of change vectors for this, and we saw that the change vectors go like this. And that when we drew a lot of them, and remember in 2D we have to draw a lot of them with very short dt's to get a good approximation of the trajectory, we saw that this differential equation, x prime equals v, v prime equals minus x, gave us trajectories which were circular. And we got a nested series of trajectories around that equilibrium point. So here we have an interesting object because this is not two 1D equilibrium points joined together. This is a truly 2D equilibrium point. And now if you ask the question, yeah, but is this a stable equilibrium point or an unstable one? The answer is it's neither. Because here, if you perturb off that equilibrium point, do you go far away? No, you don't. You just go around and around in that little neighborhood. You don't go far away. Do you come back to the equilibrium point, which would make it stable? No, you don't do that either. You go around and around in the neighborhood. So it's actually neither stable nor unstable. This is what is called a neutral equilibrium point. Then, in our second version of the spring, we added friction to the spring. And adding friction to the spring changes the differential equation so that it's now just not x prime equals minus x, but x prime equals minus x minus v, where this is the friction force. And what does that do to the vector field? Well, it changes the vector field with friction so that the trajectories now look like this. Now that, in xv space, that is a perfect example of a stable equilibrium point. It is an equilibrium point, right? X prime equals 0 means v equals 0. V prime equals 0 and x equals 0 means v equals 0. So 0, 0 is an equilibrium point. And by looking at the trajectory, we see that this is clearly a stable equilibrium point. And it's a stable equilibrium point that is not the sum of two 1Ds. You can't predict the next point unless you know both the x and v values. This is called a stable equilibrium point of spiral type. And it's the biggest and most important example. It's something we're going to see a lot. It's the biggest and most important example of a 2D stable equilibrium that is not the sum of two 1Ds. That's a really indecomposable 2D motion that's making that a stable equilibrium point. And then finally, you may recall that we talked about a somewhat fanciful example, which was the idea of negative friction. We said, what the heck is negative friction? Well, whatever it is, I'll tell you what it looks like in the differential equation. It looks like this. Instead of minus v for the friction term, we have plus v for the negative friction term. The other thing we can say is, physically speaking, friction robs the system of energy. That's why it spirals into 0, 0, because it's losing energy due to the friction term. Not happening here, but is happening there because of the friction term. So whatever negative friction is, it's going to have the opposite effect. It's not going to rob the system of energy. It's going to supply energy to the system. And therefore, its trajectory is going to look like this. It's going to spiral out, and this is therefore an unstable EP, again of spiral type. A small perturbation off the equilibrium point goes far away, so it's unstable. And so now we have these three new equilibrium points in true 2D: the neutral, the stable spiral, and the unstable spiral. And the interesting thing is, the first three that I gave you, the mix and match, and these three are all the equilibrium points that can occur in 2D. We have now completely covered the subject of equilibrium points in 2D. They are one of those 6 types. We'll talk about how to determine which, but they're one of those 6 types. We got the equilibrium points by solving this pair of equations for the x's and v's that satisfy, and then we know it's one of these 6 stability types. Okay, that covers 2D equilibrium points. That is 2D linear equilibrium points, which is the same thing. What about 3D? What about n dimensions? Well, let's think for a second about 3D. So we have x prime equals f of x, y, z. Y prime equals g of x, y, z. And z prime equals h of x, y, z. What is that going to look like in 3D? And the answer is the principle of mix and match works. Take any combination of one-dimensional equilibrium points, stable or unstable, take any number of them of both types, stick them all together, then take any number of two-dimensional equilibrium points, spirals or circles for neutral, take any combination of 2Ds and any number of 1Ds and stick them all together, and you have a legal equilibrium point in n dimensions. For example, let's look at a system that has a 2D stable spiral. No, you know something? I'm going to do a 2D unstable spiral. And in the z-axis, I'm going to have a stable equilibrium point. So in the xy, here's my origin. In the xy, the system is going to be an unstable spiral. And then in the z, it's going to be a stable equilibrium point. So now you take any point out here in xyz space, and it's going to zoom into the plane at 0, because this is a stable equilibrium point. So it's going to follow that to zoom into this plane. And then once in this plane, or as it approaches this plane, it's going to start spiraling out more and more and more. And so the trajectory of this system in xyz space is going to, if you started, for example, here, you would be zooming in here, and then as you zoom in here, you start oscillating wider and wider and wider as you come into that plane. So that's an example of a simple mix and match with a 2D stable spiral and a 1D stable equilibrium point. Any combination of those is going to be a legitimate equilibrium point in 3D. And while we're on the subject, we might as well generalize to n dimensions. And in n dimensions, it's exactly the same thing. all equilibrium points are linear equilibrium points. Take any number of 1Ds, any number of 2Ds, stick them all together, and you have a legal equilibrium point in n dimensions. So we totally understand linear equilibrium points in n dimensions. And we also have this very powerful principle called the principle of linearization, which tells us that all equilibrium points, the biggest, ugliest, nonlinear 16-variable differential equation, at each equilibrium point, it's going to be one of the elementary equilibrium points. That is the principle of linearization.